Hey, good afternoon, everyone. Good afternoon.
Hello, good evening,
Good evening.
Professor.
How are you? Good evening. Good evening, Malaysia. All right. So I see four people, and we have actually 17 people on the roster. There were 19 people originally on the roster, but two have never attended, and they dropped out actually. And there are a couple of more people who have never attended any class, but they are still on the roster because that means they haven't taken any of formal step to withdraw. So I don't know, so as far as the roster is concerned, 17 people, but normally about 9 people attend. Now, so how are you, Rostam? How are you? Um, All right. So I said we were gonna do the Excel exercise, right? Hello, Michael. Michael Rocha just joined us. Um, so I said today we're gonna do the uh, Excel example, right? So which means, okay, let me go to the course materials, and I want you to all open this file, download this file, okay? Download this file. And oh, listen, and it will be easier, right? If you have two screens. So some people might say, well, I don't have dual monitor, or I don't have dual monitor, or I don't have two screens, I don't have two computers. How can I do that? Well, you can do it this way. First, you can use your you can use your phone. I mean, if you don't have two computers or laptop, or if you don't have, if you have a laptop and a notepad, what's that called? iPad, or you have two screens, right? If you have, if you don't, at least you have a laptop or a computer, and you have your phone. So you can use your phone to log into the Collaborate, right? And but on your laptop or computer, you must download this file first. Okay. Uh, Michael, no, there's no homework, but there is quiz one coming up, right? Quiz one. The announcement went out already on Monday. The quiz one is coming up this Friday. Uh, and that's the most important thing. Where was I? Oh, so download this file on your computer or on your laptop, and because you can only log in only through one device. I mean, you cannot. I don't think you can log in. I mean, if it is possible, I haven't tried. I haven't tried, but if it is possible to log in, but I don't think simultaneously on your computer and on your phone, then that's better. But I don't think that's technically possible, because with only one account, you can only log in once through just one single device, right? Because, um, but that's just my rational thinking that technically if it is possible or not, I don't know. So the safe idea is that you first download this file to your computer, and then through your phone log in. Maybe when you try to log in, then the site might say you already logged in. Then that means you will have to log out from the computer and then log in through your phone. Okay, everyone understands? Anna has joined
Hi,
us.
Professor.
Hi, how are you?
Good. How are
So,
you? I'm a little lost as to what we're talking about. I couldn't hear anything this whole time for some reason.
oh yeah, yeah, you just logged in, so you didn't. So I was just explaining because we are going to do the Excel exercise, right? We're going to do the Excel exercise. Everyone needs to download this file. And two, because you cannot simultaneously watch the screen and do the exercise at the same time, you will need two screens. However, since most of you don't have two screens, I mean, some of you may have a computer and a laptop, or a laptop and a notepad, iPad. If that is the case, wonderful. But if not, at least you have your phone. So, and technically, the site won't allow double logins by the same person, right? You have only one account. So if you are already logged in, if you're already logged into Blackboard through your laptop, uh, and when you're trying to log in through your phone, it won't allow you. I don't know how it's gonna, like, I have never tried it. Technically, but that's my logical thinking, because technically, no sites, no allow uh, two double logins or multiple logins by one account, right? It's not like your bank. If you're using your mobile banking, I mean, you use your phone at the same time. If someone is trying to log in, if you're trying to log in also on your computer, it may not allow that. Or in that case, it would be different, because it would be a different story, because your mobile app is a different thing from your just web page of your bank. However, if they are using the uh, same site, right? In our case, if you're already logged, because Blackboard, I don't know the mobile app, and there's a difference between mobile app and the regular website, but you can try. But the safest thing is if you are trying to log in through the phone, then you might have to log out of the computer. But that's why I'm saying you must download this file first on your computer. So then, if you did that, you have this file on your computer, and you can watch the screen. You can watch what's going on your phone screen, on your phone, right? Of course, if you have a very small phone, that screen won't help that much. But if you have a decent um, screen size on your phone, then you can follow. You can follow what's going on. So that way you can watch and do the exercise at the same time. Okay, everyone is clear about that?
Yes.
Okay, all right. So then let's do this. Okay. Looks like Brandon has a question. Brandon, do you have a question? Your microphone is on. Okay, you don't. I would assume you don't, so I will mute you just in case. All righty. So if you have all downloaded that file, and open it, please open it. And no problem. I just muted you from my end. All righty. So if you okay, the file is open now, and this is something you saw already on yesterday, right? Something you saw. We'll just backstab it, or we'll just simply do it this time. So first, Yeah, okay. uh, I have two screens open, so I'm getting actually I'm getting uh, confused which screen I should. Okay, so this one we have the we don't have the verbiage, but we are quite sure. We know very well about the narrative. We know the narrative of this model, isn't that right? Your principal is $10,000. The You put it in the bank, and the bank pays you 10% annual rate, annual interest, and you keep it there for 10 years. And this is compounding frequency. Compounding frequency in this example is annual because it's once a year. In this case, compounding frequency is quarterly, right? 4 times a year. Now, we're gonna. I know you would like to do this first, but let me do this first. Let's do this first, right? Okay. So uh, those who have just joined us, you missed. I gave this instruction already twice, so I'm not going to repeat it again. So if you don't know what's going on, please ask Anna. Okay, Anna, please. If anybody asks a question, about
Okay.
how to use dual screen. I mean, if you don't have dual monitors, using your phone, and doing your work on your computer, right? Using your phone to watch, and so first, so it's asking for the future value, so it's obvious, we just follow, right? We just follow this formula. So principal times 1 plus APR adjusted for compounding frequency, right? Raised to, so APR is 10%, but since it is quarterly, it's going to be 2.5% per quarter, right? It's going to automatically take care of that. And then how many compoundings? There are, for 10 years, there will be 4 compoundings a year. So there's going to be 40 compoundings, right? C3 times D3 will take care of that. Okay, there you go. So this is going to be the future value, right? So, and then what about this? We can simply copy this and drag it over, right? Copy this and drag it over there, right? So when the compounding frequency is annual, if the compounding frequency is just once a year, obviously, you the future value will be smaller, right? And another thing is, you might wonder, we can arrive at the same. Uh, did I do this here? Oh yeah, yeah, yeah. I used Excel's built-in function, but I'm not gonna give you that because that's I actually want to anybody wean you from, um, if anybody is just used to using Excel's built-in function, I want to wean you away from it because you're just a data puncher. If you are using Excel's built-in function, you're turning yourself into a data puncher. Nothing but data puncher, not without thinking. Now, this one, I can also do it like this because, compounding is annual. It doesn't really matter, right? Uh, you don't need to make any adjustment because compounding is annual. However, we will still get to the same result. Now, there's no point in dividing it by 1 or multiplying it by 1 because it's the same thing. However, You get the same result. However, I prefer doing it this way because this way it's uniform. Everything, if you're doing like 10 problems like this, a dozen problems like this, right? You don't have to do it one by one. By having a uniform structure, you can just copy and paste. And dozen problems are taken care of by a single stroke, right? So that's the efficiency, and that's why we use Excel. We don't want to do it one by one. So here, as I said, because D2 is 1, actually it makes no difference. However, having this structure, which seems more complicated than this, has no downside. It has no downside. It's totally harmless, totally innocuous. It only has uh, uh, it only has upside, right? Because we can handle 100 problems like this. If you put them all, if you stack them up in one table, you just do the one problem and just drag it down, right? And with just a single stroke, you can solve 100 problems all at the same time, right? So structural uniformity in the model is very, very important, right? Okay. Now the next question, this time, instead of, see, I made adjustment to the APR and T inside the formula, right? Here, I'm making that adjustment outside the formula, right? Um, because anyway, what is this? I mean, uh, uh, okay, okay. What is APR over M? That's R, the periodic rate. What is M times T? That's N, total number of compounding, right? So instead of making adjustment inside the formula, I'm making that adjustment outside the formula. And uh, this makes formula, this simplifies the formula, right? This simplifies the formula. Of course, then 10% over this, and which is this times this. Okay? Now, then we know what it's going to be. We're going to have exactly this future value here, right? This time, it's going to be just principal times 1 plus r, the periodic rate, raised to n. Okay, we got the same. Now, we don't have to do this one by one. It's all the same structure. All you need to do is bring your cursor to this southeast corner, and when this cursor turns to normally, this thick white cross, when it turns into a thin black cross, you just gently hold down the left mouse button and just drag it down. And everything is done in a single stroke, single stroke, right? With a single stroke. So everyone got the same result? Hmm? Everyone got the same result? And last but not the least, as I dragged it down, This borderline got erased, so I'm going to put.
Professor, can you do it again, please?
Do what? This one? This one?
The first one.
First one? I mean
No, no,
this.
no. The one that you were doing.
This one.
Yeah, please.
Well, basically, first, I found the periodic rate, which is basically the definition of the periodic rate is this, right? And I found n, the definition of n is this, right? So I found the future value exactly by the structural definition of future value. Principal times, right, open parenthesis, 1 plus r, close parenthesis, raised to n, right, done. And once it's done, I highlighted these 3 cells, right, and placed a cursor here, right, this corner, right? If you bring the cursor to that corner, the cursor turns into thin black. I don't know. It could be a plus sign because plus. So you are duplicating, right? And when it is, when you see that thin black cross there, right? When you see that thin black cross there, right? Just gently hold down the left mouse button and just drag it down. All right? Did you get that?
Yes, Professor, thank you.
All right. So everyone got the same result, right? Please confirm.
Yes.
Okay, good, good, good. I'll take it. I'll take it as yes from everybody. Where is my? Okay. Yeah. Now next question is about the discounting, right? The first one was about compounding. Second one is about discounting. So this is your expected future value. I mean, you want to have this future value 10 years from now. And currently, the bank interest rate is 10%. Um, and compounding happens once a year. And this one, compounding is quarterly, annual and quarterly, right? So just like the previous example, I want to do this first, okay? So basically, principle is future value divided by 1 plus R. R will be APR divided by M, close parenthesis, raised to T times M. Okay? So then that should be 10,000. And they conform, they comply with each other, isn't it right? Because this example is exactly the reverse process of this, isn't it right? So if you're solving it in reverse, you have to arrive at 10K. Also, in this case, the same thing. However, I'm not gonna do it again. I'm just gonna drag it up, right? And the formula is exactly doing that. Now, I can do the same example, right? By having, right? Um, by having, so let's do this first, right? Having, R and N in separate columns, right? Uh, so we are putting, a column of periodic rate and N outside the formula. So of course, if you divide this by, I'll do this first. If you divide this by this, it's not dollar, it's not dollars, think about it. It's percentage, right? But do you leave it like this? No, you don't leave it like this because Excel is in this, generally Excel is normally set to round it to an integer. But if you let it round to integer, we know it is 2.5%. So although you know it should be 2.5%, but someone who doesn't have any idea, any prior knowledge about this problem, would really think it is just 3% even, right? So you don't want that to happen. So what do you need to do? Always give at least 2 to 3 decimal places. Give it 2 to 3 decimal places, okay? And then this one, of course, N would be, we all know. Right? So, I don't know why this is it bold? Oh no, it wasn't bold. Why did it? Anyway, why did it look like bold? Because it was Georgia. Okay, doesn't matter. So if you drag it up, right, and it makes sense, right? Isn't it right? If 10% annual compounding, then the periodic rate is still 10%, right? Total number of compounding will be 10. Now all you need to do is simply future value over 1 plus R raised to N, right? Then you should drag it up, still get it, right? All right, everyone got the same result? Please confirm. Everyone got the same result?
Yeah.
Okay, only one person? Only one person? Rustam says yes, okay, good. 2 people only. Okay, I think Anna put something, dropped something in the chat box. Please check it out. All right, and then next, now this time the unknown is the interest rate APR, and so in this scenario we can tell, you have $10,000 and you want to grow it to $30,000 in 5 years, 30K. Compounding frequency is once a year or annual. The same example here, now it's quarterly. Compounding frequency is quarterly, right? So you have $10,000 now, you put it in the bank, and in 5 years, you want to grow it to 30K. So what should be the annual interest rate? annual interest rate. The question is in annual interest rate, right? Okay, but first think about it. This one we will have to, you'll need to find, because compounding is quarterly, you need to find first quarterly rate, and then you'll need to convert it into an annual rate. So let's do this first, because once you can do this, this is just, piece of cake. And we know the formula. I mean, this is the geometric average formula, right? In scenario 1, only in scenario 1, because in scenario 2, you cannot use this formula. This formula is generally called CAGR, compounded annual growth rate, but I don't like that name because it doesn't have to be annual. It can be used for quarterly, daily, or whatever. The CAGR is generally the name they use it. But if this is not scenario 1, if it is scenario 2, like when there's cash flow, right? Then you have to use the other formula, right? Remember, the product, right? 1 plus r, right? 1 plus r raised to n, right? The product, formula for product, right? Well, let's do this first. So basically the formula is, right, future value or present value, right, raised to 1 over n. Don't forget, n is not 5, n is 20 because it's 5 times 20. Again, you don't want to do it, you don't want to hard code it, right? Avoid hard coding, because if you hard coding means, hard wiring. Hard coding cannot be reapplied because it's already hard wired to that context, right? Always use soft coding. So t times n, t is C24. Normally I just click it in, but this time, if it is like this, you can't type it in. You can't click it in, so I will have to type it in. And it is D24, right? And the parenthesis there, you need that because otherwise 1 over C24 will be done first. So to prevent it, you will need to have parenthesis here, okay, and then close, and then minus 1. Okay, it's this one, right? And if you hit enter, this is not annual, right? By annually 5.65%, you cannot triple the money in 5 years. So obviously, what we did here is quarterly rate. So how do you convert that into annual then? Because the problem is asking for annual. Label is annual, right? This is something you have to pay attention to, but most students don't have that, tenacity to stick to the specification of the problem, right? But that tenacity and attention to detail, that's what makes the difference. So because this whole thing is the annual quarterly rate, all you need to do is multiply it by 4. Again, don't enter 4 manually because that's hard coding. You cannot reapply this to, you cannot reuse this to another problem if you hard code anything, right? So Where is 4? 4 is in D24. You just, click in or type in D24, but since you cannot click it in, just type in, hit enter. Now that's more like it. That's annual, right? Annual rate. Think about it. It has to be at least something like 23% a year to triple it in 5 years, right? It stands to reason. I mean, common sense tells you, by 5 point something percent, you cannot triple the money in 5 years. Now, if you did this, then it's simple. All you need to do is copy and, I just copied it. Where did it go? Copy and paste. And that makes sense. Just compounding only once, it takes higher interest rate to triple the money within the same holding period. Now, if the compounding frequency is higher, it takes smaller interest rate, and you still get to the same future value. If the interest rates were the same, this future value will be greater, definitely, right? But it's the same future value and the same principle, and same 5 years. The only way you can get to under different compounding frequency, the only way this can get you to the same future value is by a smaller interest rate, right? Or the only way, with only annual compounding, the only way you can get triple this money during the same period is by higher interest rate, right? All right, and then what about n? Finding, how many years? I'm going to do this first. First of all, the formula we talked about, this is why we had spent so much time on natural log, right? Which is, based on Euler's number. And without understanding what Euler's number is, you don't understand what natural log is, right? So using that formula, right, which is natural log of FV over PV over natural log of 1 plus. Now, this is annual rate, but we have quarterly compounding, so we need to divide it by D25. Right? There you go. Once again, this is not, you shouldn't stop here. I mean, if you stop here, you're giving inconsistent answers because we know what the answer should be. It should take 5 years, right? So why? This means it's 20 quarters because we solved the quarterly compounding problem. So we need to convert it into years. And converting this into years is simple because this is 20 quarters. All you need to do is divide it by 4, which is in D25. You're going to get 5 years. And if you did that, all you need to do is copy that and paste. Just paste. You'll get 5. Again, because in this case, compounding frequency is 1 annual, you can just ignore m and just do Well, FV over PV divided by natural log of n plus this. You still get the same thing, right? You'll get 5 years, right? However, what did I say? Structural uniformity. Structural consistency and structural uniformity is very important. Structural uniformity, right? Because you don't want to do every problem by different formula or different structures. If you have to do it, if you have to solve, that's elementary school. If you have to solve every problem by different ways, in different ways, there's it's totally ugly. I mean, it's not beautiful. It's inconsistent and it's inefficient and it's not uniform. I mean, structural. Um, but elementary school kids will be doing that. The problems will be all of the same structure, same pattern. If the problems are of the same pattern, you can benefit from the uniform structure, right? The solution, that's what the modern civilization is all based on. Replicability, right? What is mass production? Mass production is only possible because you have uniform structure. I mean, the products are all uniform, homogeneous, so they can be mass produced. But if everything must be customized all differently, then you cannot do this, right? I mean, if all it's Model T, Ford Model T, right? It could be mass produced because they come from the same mold. They all come from the same mold, same production process, same if they all come from different if they all come in different shapes and sizes, right? Then mass production is impossible. Efficiency is not possible. Now, again, it's the same example, but now we are doing it with two additional columns of the periodic rate and n. So it's not that difficult. All we need to do, we want to, if we have this already, right, pre-adjusted, right, the formula can be much simpler. First of all, okay, we know the narrative, right? We know the scenario. You want to triple your money, principal. You want to triple your 10K to 30K in 5 years, and compounding frequency is quarterly. So then, how many compoundings actually happen? It's 5 times. Or 20. And then what should be the rate? We know the formula for rate. Future value or present value raised to 1 over n minus 1. Okay? So this way, it makes our solution much simpler, right? So we got this. However, we have to answer it in APR. And all you need to do is this times.
Excuse me, Professor, can you show the formula again, please?
Okay.
Thank you.
All right. And the next question, How many years will it take? Solving for n, right? Solving for n. So here, now we know, I mean, you can divide this by this, but we know it is, the same thing as E29. Normally I would click it in, but this I cannot click it in because this formula is like hovering over these two cells. So then I will do it this way. Okay. And then I'll use the formula, natural log of future value over present value divided by natural log of 1 plus, yeah, that's not the natural log, open parenthesis, 1 plus this, and 20. That's 20 quarters, right? That's not the final answer. That's 20 quarters. Final answer, you have to, because you have to answer. I mean, if this is what the problem wants, how many years will it take? It depends on, usually, the problem will ask how many years will it take. If the problem asks for how many quarters will it take, this is the answer. But if the problem is asking for how many years will it take, you have to bring it to years. And we know how to do that, right? You divide it by m, and you got 5, right? So everyone got the same result? Everyone is okay with this? Okay, I would take it as yes. Because if you had an issue, you would have said, Professor, right? Once again, here's an important thing. So natural log and Euler's number are reverse functions of each other. Reverse functions of each other. They are reverse functions. Just like compounding, future compounding is the reverse function of discounting. Future value is the reverse of the present value. Now, so what do you think? What do you think this is? Natural log of E. Right? Can anybody give me an answer? What is the result? What is the natural log of E? Hmm? Can anybody give me an answer? Hmm? Natural log of E. Think about it. Natural log is log to base E. Isn't that right? That's natural log. Log of E to base E. Then what should it be? It has to be 1. Isn't that right? It's just, itself. Isn't that right? Because think about it. What is common log of 10? Common log of 10. It's just itself. Right? 1. Right? Log 10 to base 10. Right? Which simply means this means 1. Right? You always simply expressing a number by its exponent, right? All right. So any questions so far? Any questions? Any questions?
No.
No? Okay, good. So it's a little early, but let's take a 10-minute break. It's 6:52. So we're going to take a 10-minute break and reconvene at 7:02. Okay? 7:02. All right, let's come. Uh,
Thank you.
all right, take a 10-minute. All right, we're back. We're back. So before, I don't know if I'm, can you guys hear me?
I can.
Okay, all righty. All right. So before, okay, thank you for the confirmation, Rostam and Zaniev. Now, so before we went into break, my question was, what is natural log of E? And I told you it is 1. So also let's confirm that. Let's confirm that. How do we confirm it? I'll just, all you need to do is um, natural log of exp, because exp is the Excel's function, Excel's command for Euler's number. It's called exp because it stands for exponential function, exponential. And it's usually, when you write it like this, it's, you know, I'll have to do this first. You enter 1 there, okay, and close. See, it's 1. Now, when you write it, you write it you you would remember from from the slide, right? Continuous compounding from our previous video. Continuous compounding. I mean, future value. What's going to be the future value if the compounding frequency goes to infinity? Yeah. If this n goes to infinity, right? Remember that? And then if n goes to infinity, the future value at infinite future, right, or when compounded infinitely, it's p times exponential function r times raised to r times t. So this thing is an exponent. However, when you use exp, right, exponential function command in Excel, uh, this thing in the parenthesis is this thing in the parenthesis is the exponent. It's this, right? And because it's natural log of e, there's e to itself, that's why you do it. And then uh, we'll give you 1 because it's just itself, right? And there's going to be another exercise later, right? But for now, we're now moving on to the next topic, next video, which is a multiple cash flow model. Multiple cash flow model. Okay, so let's take a listen. Cash flow model, time value of money, right? Actually, multiple cash flow model is as opposed to a single cash flow model, and it's of course part of the time value of money model. Now, in our last class, we completely wrapped up the discussion about the single cash flow model and the possible equations that can, or equations and formulas that can arise from the base single cash flow model, which is called compounding. Now, we have moved on to the multiple cash flow model. So basically, what does multiple cash flow model mean? Well, in the single cash flow model, remember that there's only one cash outflow and one at time 0 and one cash inflow at time n, or at time uppercase T, and you understand uppercase T means terminal time. So as an example, you put $10,000 in the bank a day, and that's a cash outflow at time 0, right? And then if the market interest rate is 10%, and 5 years later, that 5 years is your timeline, so that's the terminal time uppercase T, right? And so 5 years later, what's going to be your future value? And if the future value is some X amount of dollars, it would be, of course, greater than 10,000. At 10%, if it gets compounded for 5 years, it would definitely be greater than, much greater than $10,000. It would be just, off the top of my head, if it is 10%, it would be more than $16,000 at least. Now, but anyway, that is the future value, and you will throw that money from the bank. So that's one cash inflow, right? So that's why it's called the single cash flow model. But then what would be an example of multiple cash flow model? Now, suppose you have decided to go to a graduate school, right? And then the graduate schools cost, of course, a lot of money, right? Of course, it would cost less than 4 years. I mean, if you are going to just a 2-year master's program, let's say MBA program, and the MBA program would cost as much as what an undergrad program would cost per year. So you understand, it would be at least about $40,000 to $60,000 a year. Then for over 2 years, it's going to be at least like $100,000, $80,000 to $120,000, depending on how prestigious and respected MBA program you are going to. But let's say that costs too much money, right? And so let's say you settle for CUNY graduate school, right? And CUNY is relatively more affordable than Ivy League schools. So let's say it is about $30,000 a year. But this is master's programs are 2-year programs. Basically, if you finish ideally within 2 years. So you have a target amount here, right? When you go to graduate school, you will need to at least $60,000. But now, how do you raise $60,000? That's the big question, right? Now, there are 2 ways, roughly, about 2 to 3 ways to amass or accumulate $60,000. But of course, you will need some timeline, right? So suppose you are a freshman right now, and you have 4 years to graduate, and then not just 4 years, but most graduate, decent graduate school MBA programs require some work experience in a large corporate structure. So if you ideally graduate in 4 years, then and if you immediately land a job in a large corporations and work up some work experience, right? Rack up some work experience for about 1 or 2 years. So at least it would take 5 to 6 years before you apply for graduate school and get admitted. But let's say ideally, right? It takes 4 years for you to graduate with a bachelor's and land a job immediately and work for 1 year. So let's say your timeline is 5 years, right? So 5 years later, that means 5 years later you will need to have $60,000 ready, right? But then how do you get to that $60,000? Well, one way you can do that is by putting some principal into the bank, right? Into a bank account. For example, if you have something like $40,000 today, put it in a bank, and if the interest rate is good, very good, right? In 6 years, it will accumulate, right? It will get compounded and accumulate to accrue to 60,000. Well, we don't know that yet, but it all depends on how good the interest rate is. But once again, we know this is not very realistic, right? Because who has $40,000 now? I mean, you're just all about 18, 19, 20, 21, at that age, who has $40,000 under your name? That's not likely, right? So, more realistic and practical option is to save every month, right? So if you let's say you get a part-time job, and from the part-time job, let's say you can save $800 every month, $800. Now, you have to save a regular amount. It shouldn't be irregular amount, or and you should be making a deposit at a regular interval. And the regular interval in this case would be monthly, right? At the end of every month. So that's more, practical scenario, more realistic, right? And well, the other scenario was, you may make a deposit, but not at regular interval. You may make a deposit once in a while, here and right, of sporadically, a deposit of irregular amount. But then that kind of that can be also considered multiple cash flow, but that is not the model we are going to pursue, because there is no predictability, right? There's no predictability in that case, because you don't know when your next deposit will be and how much it will be. So we will basically eliminate that case, and we will focus only on the case of regular amount deposited at regular interval. Now, that kind of cash flow is called annuity, right? Now, the term annuity sounds like something annual, but no, it doesn't have to be annual. It can be monthly, it can be weekly, it can be quarterly, it can be daily. The point is, annuity is a payment or deposit made at regular interval in the same amount all the time, in constant, okay? So think about it. If you are saving through annuity, right? So in the first month, you make $800 deposit. And since your timeline is 5 years, there are 60 months, right? And then you make a deposit at the end of the first month, at the end of every month. So then the first deposit will, until the month 60, right? It will earn interest, monthly interest, right? Compounded 59 times in total. Isn't that right? Because you're making a deposit at the end of the year. Now, the other model is called, this is called, I'm sorry, I forgot to mention the name of this type of deposit. It's called ordinary annuity. Ordinary, because it's called ordinary, right? Making a deposit or payment at the end of each year, right? Now, and this is more likely because you cannot make a deposit at the beginning of the month. Why? Because the money you deposit comes from your paycheck from your part-time job, right? And you get paid at the end of the month, or you get bi-weekly. That means you're getting paid at the end of each 2 weeks. So you cannot make a deposit before you get paid. I mean, you cannot get paid before you start working, right? So there's no way you can make that deposit at the beginning. Of course, unless you make that deposit out of your own pocket, right, from the money you already had. But let's say you don't have anything, you don't have any money in front, in advance, so the money has to come from your paycheck, right? Then this deposit will start from the end of the month. So that's why there will be 59 compoundings of monthly interest rate, right? Think about it. If the interest rate, you're making a monthly deposit, and if the compounding is monthly because you're making monthly deposit, right? Each month, that $800 that you deposited at the end of the first month will earn interest every month until the end of your timeline, which is the end of month 60. But since you started from the end of month 1, there will be 59 compoundings until the maturity, right? Make sense? Now, that type of, okay, so this, let's just, quickly go over our scenario again. Our scenario is you're making a deposit of $800 for 60 months, and the first deposit will be compounded 59 times. That means then second deposit will be compounded 58 times, and so on. Now, just roughly, let's do a rough thought experiment. I mean, all these $800 alone, there will be 60 deposits of $800, right? That alone will be what? $48,000, right? 800 times 60, $48,000. That's principal alone, right? But this is not made at time zero. This is not deposited at time zero. It's spread over 60 months, right? So think about it. With $48,000, with good interest rate, it may be able to your future value or the maturity value to 60,000, right? But just to make it more manageable, because 60 months is, it's very tedious. I mean, it's not that long, but it's very tedious to actually to work with. Let me
bring it down, scale it down to a smaller example. Now the first, okay, let's take a look at this slide. The title is FVA. What do you think it stands for? It stands for future value of annuity. Okay, and then I'm going to get to the other one shortly, but first let's take a look at this scaled down version, right? Scaled down example. In this example depicts an annuity, annual deposit, annual annuity of $1,000 at the end of the year for 5 years, right? Then our question is, what's going to be the total amount or the future value of this annuity at the end of year 5? Now, let's take a look. If the interest rate is 20%, right, the first deposit, 1,000, will earn interest, right, 4 times compounded. So that's 1,000 times 1.2 raised to 4. Because there will be 4 compoundings until the maturity, right? 1, 2, 1, 2, 3, 4, right? Second deposit of 1,000 will earn interest 3 times compounded. Third deposit will earn interest 2 times compounded. Fourth deposit will earn interest once. And the last deposit is only technically called deposit, but if you think about it, you're making the deposit at maturity. So that means, it's almost like, dipping your tortilla chip into the salsa and just take it out. The minute you, right, the instant you put the money in the bank, you take it out. So there's no time for the interest to accrue on this deposit. Make sense? It's like, dipping the salsa, but take it out so quickly, there's no time for the salsa to, stick to the tortilla chip, right? Just like that. So then think about it. The total amount will be, right, the first $1,000 deposit will earn interest 4 times compounded. It's going to be this. Second one will be this. Third one will be this. Fourth one will be this. And since this one doesn't earn any interest, right, it's just 1,000. And then 5 years later, the total of that will be this. Okay? That's the future value of annuity. Now, this is ordinary annuity because all these deposits are made at the end of the year, right? At the end of each period. Now, let's take a look at another example. And in this other example, also scaled down version, right? This annuity starts from the beginning of year 1, so time 0. So in this example, you're making a $5,000 deposit or payment. I mean, deposit and payment it can be called interchangeably because they are eventually the same thing. Just, turn the table around. Deposit is payment. Anyway, so first $5,000 deposit earns interest, 10% interest, right? 10% interest, 5 times compounded. If the interest rate is 10%, right? Look, this deposit earns interest once, twice, 3, 4, 5 times, right? And the second deposit earns interest once. Third deposit earns interest twice. Fourth deposit twice. Third deposit earns interest 3 times. Fourth twice. Even the last deposit earns interest once. Okay. Now, this type of annuity is called annuity due, right? Meaning the deposit or payment is due already at time 0. In other words, it's already due to begin with, right? So, of course, the future value or the total amount, the calculation of the total amount of future value is, is simply the same. You find the future values and sum it up, and in this case, it comes to this. Now, so you might wonder, if it was the same scenario, and if this was, not annuity, ordinary annuity, but annuity due, so how much will be the difference in the future value? Now, if you think about it, if we had $1,000 here, if we had, if we started making a deposit at time 0, another 1,000, then you only have one more term, which is, 1,000 times 1.2 raised to 5, right? And then you don't have this because this one will drop out because 5 deposits at the beginning of the year, so this one will drop out. And then if you compare them, right, compare those 2 scenarios, the only difference between the 2 is actually one more compounding. Isn't that right? Haven't you found that? Because if this was made at the beginning of, right, if the deposit was made at the beginning of the year, that's going to be 1,000 times 1.2 raised to 5. And it goes all the way to this, and just, without this, right, without just this one, the last deposit. So, then think about comparing this series of annuities and with the the other one, right, with just one more. Think about it. This one has one more compounding. In other words, the first deposit has one more compounding. Second deposit also has one more compounding. Third deposit has one more compounding. Fourth deposit has one more compounding. Last deposit has one more compounding. And just ignore, think about it. The time starts from here. This is time 0, time 1, time 2, time 3, time 4, right? And there'll be time 5, but there's no deposit at that point, right? You see that? So the difference between the ordinary annuity and annuity due is one more compounding, right? Now, so then that gives us an idea. How do we calculate, how do we make it easier to calculate the annuity due? Well, we're going to also talk about this later, but that means you can recycle. If you have ordinary annuity, if you have solved it as an ordinary annuity, all you need to do is recycle this and give it one more compounding. And you might wonder, oh, why do you have to do that? Can you not just start doing this from the beginning like this? Look, this is a scaled down example. It's really a minimal scale version. Think about it. Even our scenario, even our example of graduate school fund, right? How do you raise graduate school fund, right? In that example, you are dealing with not just 5 deposits, but 60 deposits, right? It's 5 years, but not annual deposit, but monthly deposits, 60 monthly deposits, right? So how would you handle 60 monthly deposits this way? There's no, it's not undoable, right? But it's going to be very tedious if you are going to do it this way, right? This is very elementary way of going about it, right? In other words, even a 8th grader, 6th grader can understand this, right? That's how watered down the example is. But anyway, because this is pedagogically easier to convey the idea, right? This example is useful, but in reality, there is hardly a case you can do it like this. So then, how do you actually, do that? So actually, I already introduced a formula for that. Then the question is, of course, this formula is showing you that basically telling you future value of annuity is equal to payment. Payment means deposit, right? They are, I told you, they are the same. If you're at the paying end, that's payment. If you're at the if you're making a deposit and if you are saving money, right, that's deposit. And if you have borrowed money and paying back, that's payment, right? So it's just the same thing from different standpoint. So that's the deposit, and 1 plus R. This R is of course the periodic rate, the monthly rate. This N is the total number of compounding, which is 60 in our example, minus 1 over that periodic rate. Okay, we can use this formula to get to our, find our solution. In other words, how much those $800 will accrue to, right? We're going to get to that soon. But let me switch to, let's build that concept from this assumption, right? Very simple diagram. And let me switch that switch the screen to a whiteboard. So let me start sharing this screen and switch to whiteboard. Start with the right. In other words, future value of annuity, right, equals payment times 1 plus R raised to N minus 1 over R, right? And how, right? That's our question, right? So let's think about it. And this will take time. So we may come back later to actually, see how the through steps of derivation, we can see later how this formula is derived. But ignore this for now, and let's see. So let me erase this. Ignore this for now, and let me start from the very crude concept, right? So future value of annuity is like, think about it. First of all, the first deposit, right? Once again, payment is deposit, right? Will earn interest by the time you reach your future, which is 60 months later. The first deposit, monthly deposit, that's monthly, will earn interest how many times? it will earn interest 59 times in our scenario. Isn't that right? You remember that? 59 times. Why 59 times? Once again, because you're making a deposit at the end of the month. Counting from that point, end of the first month is the beginning of the second month. So counting from that, it will be a 59, not 60. So in here, I'm not going to write it as 59, but write it as t minus 1 raised to t minus 1. So the uppercase t is what? That's the terminal time. So in our example, it will be 60, right? So t minus 1 will be 59. And then the second deposit will earn interest. One plus r, right? Sorry, r here, raised to t minus 2, right? And we know what then the rest of it is, and that's going to be the third deposit will earn interest, t minus 3 times, so ellipsis, and then, next one, as we move closer to the end, right, to the terminal time. Now, the third from the last deposit will earn interest 2 times, right? And the second from, sorry, that must be payment, right? That P. And the second from the last will earn interest. So difficult to write with, mouse. It will earn interest at least once, right? Plus R. And the last deposit, I told you, last deposit, this is like 1 here, right? We don't have to write 1. The last deposit doesn't earn any interest, right? Because you are making that deposit at the end, and at the end of month 60. And when you make a deposit at the end of month 60, you will just, take it out right away, right? But also mathematically, you can write it as 1 plus r raised to 0, right? You understand what that is? Remember, anything raised to 0 is what? 1, isn't it right? So that means this term, although it is there, eventually it is just 1, isn't it right? That's only 1, right? So if it is 1, anyway, this thing will just reduce to just payment, right? You get that? Now, however, this is a very tedious way of writing it because, look, I just used ellipsis. That means I truncated in the middle, right? If I didn't truncate it in the middle, what does that mean? I will have to write it all the way from t minus 1, 60 terms, all the way from here to, all 60 terms. Now, that's called a polynomial mathematically. Polynomial means literally many, right? Nomial means, terms, right? That means, multiple terms, polynomial, right? So that is very tedious to write it this way. So we know better. Is there a better way we can do this? Yes, of course. We use summation sign, right? Summation notation, right? And so we're summing up all payment times 1 plus r raised to n, where n runs from 0 to t minus 1, terminal t minus 1, right? You get the idea then? This is a very nice way of making that long polynomial very compact, right? It's a nice way of expressing in a very long polynomial, repeating, right, recurring terms in a very compact way, right? So think about it. 0, that's this, right? It becomes this. When n is 1, it becomes this, right? Because n runs from 0 to t minus 1, and you are summing them. When n is 2, it becomes this, right? When n is t minus 2, in this case, 60 minus 2, so 58, it becomes this. When n is t minus 1, it becomes this, right? When n is 59. So you're summing up all of them. Now, so that's nice, right? In other words, it's going to be, this is going to be $800, and this interest rate, if the interest rate is annual rate is 6%, we know what this is going to be. It's going to be 0.5%, right? It's not. So then our next question is, oh, that's wonderful. That's nice. We can nicely capture it in a very compact expression. But then, does it really help us actually calculate our future value? That's another question. Why? Because if you actually plug in the number here, right, $800 times 1.05 raised to 0 raised to 1, when it is just $800, right? But that means you need to run this all over again. You have to actually do this all over again. This is, in other words, then what does that mean? Now, this is only a nice way of compressing, right, in a succinct, expressing this in a succinct way. It just doesn't, but it doesn't really help us to calculate, right? You understand? So then, how do we calculate it? So we have to use the reduced form, which is basically payment times, right, 1 plus r raised to n minus 1, okay, over r, right? Now that's the formula we need to use, and this is reduced. I mean, this formula doesn't just drop from the sky. It just doesn't pop up from the thin air, right? There are steps of derivation. This one is derived basically from this, and there are steps of derivations. I will not show you at this time because it will take a lot of time to. It will take about 10-15 minutes, but we're going to get to that later. But right now, we want to use this formula to actually solve our graduate school fund question. Understand? Okay. So let me switch back to an Excel file. Okay. Okay. So let's see. Okay. Do you see this Excel file? Okay. Now this is, of course, this is the file we've been working on previously. We were on single cash flow model, right? This is the time value of money, right? And previously we were on single flow. Now we are on multiple cash flow. So you need to, you gotta, click on this bottom tab that says multiple cash flow. Now, when you open it, maybe these cells would be already filled in. So I want you to clear out all the highlighted cells when you open it. Okay. All right. Now let's think about this. This is exactly our example, our graduate school fund example. You recognize that? You all recognize that? Because this is your monthly payment or deposit, right? And your APR, the prevailing market rate, is 6%. Your timeline is 5 years. M is 12, right? M is 12. That's monthly, because it's monthly deposit. Then what do you need to do? We will need to first find the periodic rate, the monthly rate, and how many compoundings actually happen over 5 years, which is something we have done already previously. So it's not difficult. You just divide 6% M, APR by M, gives you 0.5, and 5 years times 5 times 12. Of course, everybody knows this is, even a second grader can tell, third grader can tell, right? 60 months, right? 5 years is 60 months. Now, future value of annuity, you know the formula. The formula is there, right? We did that. So all you need to do is payment times or deposit times, open parenthesis, 1 plus r is to n minus 1, close parenthesis, and divide by r. Okay? Hit enter. We got that. And some of you may say, some of you got excited and say, hooray, we got it. No, we got it, but that's not the final answer. Why? What was our question? Our question was, you want to go to graduation in 5 years, and it will cost $60,000, right, to finance your, to pay for your graduate school for 2 years. So our question was, if you work part-time and save $800 every month, you accumulate enough money at the end of year 5 to pay for your graduate school. So that is that is your final answer. Is that enough? I mean, did you reach the target future value, right? You had your target future value, which is 60,000, right? So arriving at this is only half the answer, right? You shouldn't lose focus. You shouldn't lose the perspective, right? The reason you calculated this is to see whether you can reach the target future value. So you have to answer that. Oh, of course not. This doesn't come to your target future value. In other words, it still undershoots your target future value by about $4,000. Okay, then how do you, to reach that target future value, you have to try out different scenarios. In other words, different strategies, right? One possible strategy is increase your monthly deposit, right? Another possible strategy is find a bank that pays higher interest rate. Okay. Still, another strategy is, what if you extend your timeline, right? You extend your timeline by 1 year. Okay. See, there are three possible different scenarios, then, right? In all these different scenarios, you can compare with, in a single shot. That's the beauty of Excel, because you don't have to do it one by one. Now, all you need to do is simply, because they are all using the same formula, you simply highlight these three cells at the same time, right? Select these three cells simultaneously, right? And then you can drag it down simultaneously, and then all of the results are automatically calculated, and so you can compare them in a single shot. And then this is, as I said, this is the beauty of Excel. You don't have to do them one by one every time, right? Now, the second scenario, right? Second strategy. Now, if you increase it by $50, you got a lot closer. You're still about $700 short, right? So that means you are close, right? So it's only a matter of increasing, fine-tuning, right? But again, fine-tuning will require trial and error. In other words, you'll have to try out different numbers. It's called trial and error method, and trial and error is still a very crude method, because it is not very time and resource efficient, right? You have to put in your time to try out different other values, right? And we don't know how many trials it will take to nail the exact 60,000, right? Now, the third scenario, higher interest rate. Now, 8% it may not seem very impressively higher than 6%, but in a banking industry, right, in a financial industry, 0.25% difference is a huge difference, right? Banks, as I told you, banking is a very competitive industry, right? You really don't find another bank that pays a significantly higher interest. Significantly higher means something like greater than 0.25, 0.5, right? So this is almost unrealistic. But just for our thought experiment, we can do that. And even if they are paying 2% higher, we are closer, but we are still about $1,200 short, right? What if you extend your timeline by 1 more year? Well, then you more than overshoot, right? You more than reach your target future value, right? You even more than reach it. You overshoot it by 9,000. Well, this is wow. I would like that. I mean, I would. Of course, who doesn't like this? But then means you're postponing graduate school by 1 year. Well, if it doesn't matter, that's fine. But if it matters, then that's the other story, right? So our next question is then, is there a way we can nail the exact payment, right? Instead of going through trial and error, can we nail the exact payment? Yes, we can. We'll definitely talk about it later. But here, what about this column? The column H is the column of annuity due, right? That lowercase d at the end stands for annuity due. Okay. So how do you find annuity due? Well, didn't I tell you when we were doing that? When I was showing you that scaled down version of example, the only difference between ordinary annuity and annuity due is just one more compounding. So what does that mean? You can recycle the ordinary annuity result, right, and simply give it one more compounding. Right? Simply give it one more compounding. It makes sense. So if you do that, that's annuity due. Is drag it down. Okay, we get our future value by annuity due. Okay, alrighty. So well, that's the first part of this lecture, and then we will need to take a break and.
No, we're not, because we've already taken a break. We'll keep going to the next video. But any questions so far? Any questions about the future value of annuity? Any questions? Hmm? Of course, after the present value of annuity, there will be another. I will ask again if you can um, form form your thoughts, form your questions, and answer it then as well. So the next future value of annuity part 2. Now these are 1 hour long videos, right? So previously, so they take quite a while. Hopefully, we'll get somewhere. We'll get something done.
Part 2 of the multiple cash flow model, future value of annuity. Now, in our previous video, or the previous lecture, we discussed how to find the future value of annuity, right? And our example was the graduate school fund. And we tried, basically we found what would be the future value if we make $800 deposits every month at 6% APR for 5 years, right? So that's an annuity, right? Because $800, a regular amount of, or constant amount of $800 is deposited at regular interval of monthly, right? Earning 0.5% every month, right? So that's a typical example of annuity, right? That's exactly the definition of annuity. And the future value is 55,000, right? 816. But that's not the final, that's not the conclusion, right? That's only part of the solution. The reason we did this is to check if we could achieve our target. And our target was 60,000, right? Remember that? Because the graduate school 2-year program would cost, at CUNY, would cost $60K. So since we were falling about $4,000 short, so we were exploring alternative strategies. And one of those alternatives were increasing the monthly deposit or monthly payment, or finding a bank that pays better interest rate, or extending the timeline by 1 year. And we could simultaneously compare and evaluate and compare those 4 different strategies. And our next question was, and although we could easily tell, well, if you increase the monthly deposit by $50, you got a lot closer to your target, right? You're just still about $700 short. Now, also, if you increase your timeline by 1 more year, right, then you more than achieve your goal. You overshoot the goal by $9,000, right? About $9,127. So our next question was, is there any way you can exactly nail that monthly payment? Yes, of course. You can nail the monthly payment, exact monthly payment. Now, remember in single cash flow model, we solved that base compounding equation. We solved it for 4 different unknown variables, right? So just like that, we can solve this equation, right? In other words, I'll get back to we can the future value of annuity equation. We can solve this equation for payment, right? In other words, so we have 4 variables here, right? Payment, or, and FVA, right? Now you might wonder, isn't it APR? 4 variables are payment, APR, T, and FVA. Eventually it will be this APR and T, but our relevant rate and N compounding periods are these, right? Monthly rate and 60 months, or 60 compoundings, right? So you need to solve, you need these. R and N are relevant variables, right? And later, once we find them, then we can convert it to APR and a number of years, right? So let me switch to whiteboard, right? And then let me switch to whiteboard because I need to. Okay. So do you all see this whiteboard? Okay, now let's do this. So the formula is future value of annuities. Okay. Well, we wrote it like this, right? But this is also, with training, you will develop the eye to see, you know, that x equals y times, z equals x times y structure. 1 plus r raised to n minus 1. Okay. Close parenthesis over r, right? Now, you remember, what did I tell you? In all solving, you know, any equation, right? In all equations, you know, in any situation, solving an equation is basically depending on solving an equation depends on your ability, right? Your keen eye, analytical eye, that can identify z equals x times y structure, right? And of course, not everything is given already in this structure. To identify, to spot this structure, you should, if the given structure of the equation is very complex, right? You should be able to reduce that structure, the complex structure, into this structure. Now, that involves a lot of simplification. You will need to simplify the complex equation, right? You know, regardless of how many times, right? You must simplify to the simplest form. In other words, reduce it to the simplest form, and the simplest form should eventually come to this, right? Then again, solving, if x is the unknown, solving for x is very simple. It's going to be z over y. Now, then here, can you identify z equals x times y structure? Oh, you might wonder. Oh, I don't see z equals x times, but, you know, it looks like, you know, z equals x over y. No, you can look at it that way, but that doesn't help, right? But look, this is already given in. It is already in the structure. If you think about it, it's like payment times, right? One plus r raised to n minus 1 over r, right? Isn't that right? It is already given in this structure, if you think about it, right? This is x, right? This is y. Now think about it. And besides, because in multiplication, right, you can split it any way you want, right? As long as you cannot split this term because this is, you know, one whole term, right? One single whole term, but you can split it either like this times this, or this times this, right? But of course, the other case, like splitting it like this times this, doesn't help us, right? It doesn't help. So because, you know, what we want to know is payment. You shouldn't lose the sight, right? You shouldn't lose the perspective, right? We want to solve for payment, so we have to make payment our x, right? So we split it this way, and of course, you know, I doubt anybody, you know, I doubt there's someone who wouldn't understand this, because if you have let's say 8 over 2, right? It's the same thing as it's the same thing as 4 times 2 over 2, right? Isn't it right? And it's also the same thing as writing, like, you know, 4 times 2 over 2, isn't it right? And of course 2 over 2 is 1, so it's going to be 4 anyway. That becomes, you know, that's why it is 4. So you can break it up like that, right? You can break it up like that. That's the idea, right? Righty. And then we are, you know, ready to solve this for payment, because now it is z equals x times y structure. So solving for payment, what do you need to do? You will need to divide this by this, right? So payment then payment is equals, right? Payment is equal to FBA divided by the thing in the bracket. I'll just call it the thing in the bracket. Now, you all know dividing by something is the same thing as multiplying by the reciprocal of that thing, right? Remember? And the reciprocal, this is a way to write reciprocal, right? You all know what x to the negative 1 is. X to the negative 1 is what? 1 over x. Isn't it right? We did this in a couple of classes back, right? That's 1 over x, right? So we are using that. So that means, well, you're dividing FVA by this. Okay? So then it comes to FVA times, this gets very messy, so, but you know the idea, you get the idea. It's going to be R over 1 plus R raised to n minus 1. Okay? All right. So this is how you can solve for payment, right? But don't forget, right? Now let me, I just wanted to rewrite it in a neat way, but there's a limitation to how neatly you can do it with a mouse, right? So let me go back to the Excel. Let me go to, and so in a neat writing, right? A neat handwriting. I mean, not handwriting, but nicely typed up here, right? So that's our formula, right? So let's nail, okay? Let's nail it. So here, same scenario, and now this time your target future value is known. It's no longer unknown, right? Our target future value is known, 60K. So this time, payment is the unknown. So using that formula, right, solving for payment, which is FVA times R. Oh, that should be filled in, but I forgot to fill in first, but it should be filled in. But we know what they are, so we can build a formula first, and let's fill in that later, right? FVA times R over, open parentheses, open another 1 plus R raised to n minus 1, close the parenthesis, okay, and hit enter. And of course, nothing, it will say, you cannot divide by 0, right? Because this is not filled in. All you need to do is just copy that, paste here. Now, you're not copying the values, right? You understand? What is being copied is the formula, not the value, right? So so that's basically right? Formula being copied, right? Now, so we got this, but we got too many decimal places, right? Too many decimals. We don't need too many decimals, right? And we're missing $sign. This is, of course, $859, right? 9.968. So that's almost $860. So you just give it $sign, and then it automatically takes care of the decimal places, because in accounting, or in dollars, right? You are using monetary units. Generally, you don't use more than 2 decimal places. In other words, in US dollars or euro or most other currencies in the world, you don't use any lower denomination than cents, right? So it automatically rounds it up to 2 decimal places, and that's almost close to 860. So when we did this thought experiment, if we did this, a trial and error, through the trial and error method, if you plugged in 860, we would have exactly nailed it. But it's pure chance that you plug in. You have to start from 801, 802. You try all, and there are even 100 integers, right, between 800 and I'm sorry, almost 60 integers between 800 and 860. Including also not just the integers, but all real numbers, right? Like 80.05, 801.05, or 801.11. Think about it. Trying all these possible numbers, it would take a lot of time, right? And if you just first starting from integers, right, from 801 through 860, it would take 60 trials, right? So that's really waste of time. And even when you got by plugging in 860, let's say 860 won't take you exactly to 60K. It would be slightly greater than 60K, right? So then the fine tuning, so you have to try 859.01, right? Starting from that 859.02, right? Until you get to this isn't even exactly 97, it's 96 something, right? It's just rounded. So trial and error method is very time consuming, right? So not a very smart way of doing that. So but we don't have to rely on that. We can nail this. We can exactly nail this. Okay. All righty. So our next question then. You remember there are 4 variables here, and each of them can be the unknown variable. And with whichever being the unknown, we should be able to solve for that. So we solve for first future value, and then solve for payment, right? And then the next question is what? Oh, then R. How do we solve for R? The next question is N. How do we solve for N? Right? Makes sense. So then here's the thing. I'm going to show you the formula because just to save some time on steps of derivation. We don't need to derive, but eventually you will need to know how. But steps of derivation itself is not the goal, right? That's the means, right? I mean, you got to know how to do that, because that's basically the power of your brain that can derive those steps of derivation. But let me get to the let me cut to the chase. So if you're solving for R, now unfortunately in annuity or in multiple cash flow models, there's no single unique mathematical formula to arrive at rate. Okay, so what do? We'll have to use Excel's built-in function, right? Then for N, of course, there's a formula, natural log of something, future value of annuity, right? And it's a little more complicated than the single cash flow model. Well, let me show you how we do, and if there's no single unique formula for R, for rate, what we do? We'll have to use Excel's built-in function, right? Now, remember, the insert function, right? I believe I also showed you this in the single cash flow model. So go to, that's basically the mathematical notation for function, right? F of x, function of x, right? Of course, in math, to write f of x, you have to do really, f, and then in the open parenthesis, x, close parenthesis, right? That's function of x. Now, we go to the insert function, and you will find when the box opens, this dialog box opens, it's the most recently used functions that you will find in the box. And since recently we used rate, it would come on top. But if you don't see it, if you don't find it, you'll have to go into the financial category, right? And scroll down until you find rate, because rate is the name of the variable we are looking for, right? R, right? Rate. So hit OK. And then give it what it's asking for. N, right? N periods, right? So give it 60. And then payment. This is the payment. But here's one thing you have to understand. When you are using Excel's built-in function, basically it's financial calculator setting, right? And in financial calculator, there has to be a distinction between cash inflow and cash outflow, right? So which one is your cash outflow? Well, this is your cash outflow, isn't it, right? Because you're making this deposit every month in the bank at the end of the month, right? So that's the cash leaving you going into the bank. So that's cash outflow. And all cash outflows are represented as negative. It doesn't mean it's negative. It just means, it simply means it's cash outflow. So we don't want to. So we can either make this negative, or you don't have to make it negative. You can make it negative, right? You can make A8 negative. So without changing this, because when it is negative, it doesn't look very natural. I mean, in accounting, they all know negative can be expressed by in three ways: minus sign, the negative, right? Or parenthesis, or red font, right? Red font. That's But then again, that's accounting. I mean, without putting it into a red font or parenthesis, you can. This looks more natural, and you can simply by making that adjustment in the dialog box, in the menu, in the dialog box of the function, right? You can turn it into negative. Okay, so then there you go, negative. There's no present value. This thing is present. There's no present value, right? There's no present value. Because this is a multiple cash flow model, there's no single lump sum, right? At time zero, right? This whole payment is building to future value, right? And what's the future value? Future value is 60,000, right? We have it there. That's and also in notation here, there's no distinction between future value of annuity or just a single cash flow future value, because this function, right? Excel's built-in function, it should be applicable, universally applicable, so they don't have separate variable label for future value of annuity. It's just future value. And then next, type. What does that type mean? Type means either ordinary annuity or annuity due, right? Either ordinary or annuity due. Now, the default is annuity due, right? So that means unless otherwise specified, by default, it is ordinary annuity. And think about it, the term ordinary means that's ordinarily what it is, right? So if it is ordinary annuity, you either leave it as blank or enter 0. If it is ordinary annuity, leave it as blank, or enter 0. So you don't have to enter 0 because it's by default ordinary. If it is annuity due, you put 1 there. You put 1. Okay. So now, interesting thing. Why 1? You remember the difference between ordinary annuity and annuity due is more compounding, isn't it right? There's one more compounding in annuity due. So that's why you enter 1. Okay. So since this is ordinary annuity, you don't have to enter anything. And down there, guess, you don't have to take any guess, because when you entered future value, you already got this, right? You already got the result. And besides, we are nailing it. There's no reason for taking a guess. So you enter and hit OK. See, we got that. And then converting it to annual rate, we already know. This monthly, right? So monthly rate times 12 will get into annual rate. So voila, we got that. Okay. Now, next, we need to solve that for. We'll need to solve that for n, right? So to solve for n, let me switch back to PowerPoint to show you the formula, right? Okay. All right, we're back into skip a few slides. All righty. All right. Now it looks quite complicated. We're solving for other variables, n in case of n, and in case of r, right? But, of course, r, there exists. This means there exists, right? No single mathematical process, right? But in n, at least you can solve for n, right? These are the steps of derivations, and basically, it's a little more, it looks a little more complicated than the single cash flow model. But basically, to find n, you'll have to use natural log, right? And so this is the formula, right? You might wonder, what is that? Oh, well, that will come later. We're currently talking about the future value of annuity, but that's present value of annuity. So You don't have to worry about it for now. We'll come back to that later, right? So this is the formula, right? So we'll go back to Excel, okay? So for your own reference, write it down so that you can use it later, right? All right. Maybe I put it down there. So the formula is, and we'll have to, the formula we're looking for, I mean, the variable we're looking for, the unknown, is n, right? So it will be n, natural log of FBA over payment, right, times R. Now, you all know multiplying something to a fraction, right? When you're multiplying something to a fraction, it gets multiplied only to the numerator, right? So doing it like this, you might wonder if yours, oh, isn't it going to get multiplied to A9, the denominator? No, it won't get, right? To make it only, to make it multiplied only to the denominator, we'll have to put parentheses here, right? But without that, it will be automatically multiplied to the numerator, right? Okay. Now plus 1, again, plus 1, it doesn't get added to E9, right? Everyone understands PEMDAS, right? Parenthesis, exponent, right? Multiplication, division, right? Addition, subtraction, right? It operates in that order. So this gets done first, and then this, and then plus 1. So, and then natural log of that, natural log of then 1 plus R, 1 plus R here. And we know what to expect. We already know the answer. We just want to confirm that the formula checks out, right? So if you enter that, hit enter, we got 60, right? And then converting it into years, we already know 60 months. Then you divide by 12, right? 12 months, right? That takes you to 5 years. Okay, good. So we nailed also, right? We nailed also the n, right? Now, we could also nail, since I showed you the Excel's built-in function, we can do it also using Excel's built-in function. For example, let's say I don't have this, right? Using Excel's built-in function, right? So let's go to, I just don't want you to rely on that. Let's just go to Excel's built-in function, right? And if you're in the financial category, you scroll down, the variable we're looking for is future value, right? Once again, there's no distinction between future value and future value of annuity in the financial calculator. It's just future value. It's only the different, it's the only thing is the difference in the variables is inputs that are going in there. Hit OK. Then it's first asking for the rate. And the rate. It's asking for N. There you go. Payment. There's the payment, right? But once again, in the financial calculator setting, right, you have to make one thing a cash inflow and the other thing a cash outflow. And in our context, payment is a cash outflow, right? Because it's leaving your pocket, it's leaving your wallet and going into the bank. Now, there's no present value, right? This is not a single cash flow model. Type ordinary annuity unless otherwise specified. And you got this already, right? So hit OK, you got that, right? And then as you know, then scroll down, you get, right? Okay. What about this? Yes.
I guess I was not being too ambitious. I thought I could finish this today, but let's say we have about 10 minutes portion or 10 minutes portion left. But time is already 8:12, so it's not likely that we can finish everything. We'll have to call it a day at this point with only a 10-minute portion left. But we're gonna pick it up from here tomorrow, okay? And so before I let you go, let me just inform you, or maybe I'm making an announcement about Finance 100, FNB 100 classes in fall. And if you know anybody who wants to take Finance 100, or who needs to take Finance 100, in the fall, section 1100, FNB 100, section 1100, and section 1101, and section 1300, and section 1401, they all have openings. They all have openings. 1100 is, that means it starts at 11 a.m. Monday, Wednesday. This is Monday, Wednesday. 1101 also starts at 11, but Tuesday, Thursday, right? Tuesday, Thursday. 1300, that means it starts at 1 p.m. It's Monday, Wednesday. 1400 is, that starts at 2 o'clock, Tuesday, Thursday. These sections still have openings, so if you know anybody, please let them know. Please tell them to take these sections, because they are the ones that have still openings. Okay? Alrighty, so any questions so far? Any questions? Any questions?
No.
Okay, alrighty. Malaysia, only one person confirmed, but I would assume that Malaysia is speaking for the rest of the class. All right, so the class is dismissed. Have a great evening, and I will see you all tomorrow.
Thank
Okay?
you. Have a good evening also.
All right, you're welcome. Have a great evening, everyone. See you tomorrow. Okay? Stop recording.